Right. Well, on that cheerful note, I think we can go ahead and get started. Andrew, if you want to share your screen. It's my great pleasure to introduce our speaker today, Andrew Jayich. Andrew has a sort of a long and varied history in AMO physics. So he actually started out doing AMO research as an undergrad at Harvard with John Doyle, where he worked on buffer gas cooled BECs before moving on to do a PhD in optomechanics with Jack Harris at Yale. And then Andrew did 2 postdocs, one with Jeff Kimball at Caltech, also on optomechanics with optically levitated springs, and then with Wes Campbell at UCLA on using laser frequency cones to cool and control trapped ions. And then he became a professor at UC Santa Barbara. What I think you'll see, actually, if you're paying very close attention, for those loyal Vamos followers who've been watching for a while now, you would have actually already seen a sort of a sneak preview of Andrew's talk in Wes Campbell's talk. Wes included a little bit of an advertisement for Andrew's research and for his talk today. And what Wes highlighted, which I think you'll see in this talk today, is what makes Andrew's research special, is if you're like me, you sort of feel like you already see enough of radiation safety officers from laser safety, and you steer clear of the elements and isotopes that are radioactive. And what I think Andrew is showing us is that actually that may be a mistake, that there's all kinds of really exciting physics that you can do with these radioactive elements and elements and isotopes that you just can't do with stable atoms that the rest of us are stuck with. And so I really admire that Andrew's gone off in this kind of brave direction and is exploring entirely unexplored parts of the periodic table. And so with that, Andrew, please take it away.
Thanks, Shimon, for the introduction. So great. This is a picture from my lab that I think will capture for most of us what we really like about atomic physics. This is our ion trap that I'll talk about primarily during this talk. And if you zoom in on this picture, you can see at the center of this trap, spread out over several pixels, is a single trapped and laser cooled radium ion. This really gets at the levels of control that we can achieve in atomic physics, which is a large reason which draws us to the field. As Shimon pointed out, I'm working with, our group is working with an element that's entirely radioactive. And so you might ask, well, Andrew, you better have some pretty good motivation to be working with a species that's entirely radioactive. And several years ago, before we started our work, I would say, yeah, I agree with you. We really do need some strong motivations. But I would say now that we've really lowered the bar, and our lab, except for a couple stickers, looks like a normal atomic physics lab and operates like one. And we're only lowering that kind of barrier to entry more as we go further. Of course, because it is radioactive, and as I'll discuss its place on the periodic table, it really does offer some unique opportunities. I'll talk primarily about these last 2 points with the real focus on precision measurement, because I think that that'll provide the most generic, strongest motivation for our science. It's what I'm really excited about. Should say that here's Wes. What's the real reason why we're working with radium? Well, Wes came downstairs as towards the end of my postdoc and said, I know you like precision measurement. Did you know that the radium ion's never been laser cooled before? Sounds kind of interesting. That's really a testament to Wes knowing me so well, and just his knowledge of physics being broad. It really helped set up everything I'm going to talk to you about today. All right, so let's dig in. Here's a timeline of our universe. Start out with the Big Bang, and then we end up out here with all these galaxies and planet Earth somewhere. And one thing that is missing in this picture is antimatter. Okay, so our universe is basically composed of matter, and we don't really understand why there isn't an equal amount of antimatter. in the universe. So there's a massive asymmetry in the universe between matter and antimatter. This isn't explained by the standard model of particle physics. We do know that one of the key ingredients that is for this asymmetry is some time reversal violation, some time reversal violating physics, perhaps caused by new particles, at least by some new interactions with particles outside or beyond the standard model. So we'd like to set out to try and find these particles. A well-known technique for looking for time reversal violation is to look for permanent electric dipole moments. So just briefly, if we have a particle that has spin, it'll have a magnetic moment. If we reverse the arrow of time, that spin will reverse direction and the particle will point down. This is totally expected physics. If we add a dipole moment to the particle, so if we consider the particle has a permanent electric dipole moment, the dipole moment will point with some direction with respect to that spin. It'll give the particle shape. This could be an electron, for example. And if you reverse time, it's kind of like reversing a potter's wheel. That shape isn't going to change. It's going to stay, upright, if you will, if you reverse the arrow of time. And now the particle looks completely different when time has been reversed. These two spins are now anti-aligned. That's a time reversal violation and would be a hint at new physics beyond the standard model if we could measure such a moment. Okay, how would we measure a moment like this? Well, this type of moment could occur, a permanent electric dipole moment could occur in a nucleus. This is the spin vector and the dipole vector. How would you do this? Well, you want to put the dipole moment in a large electric field and then measure some energy levels associated with this system in this configuration. And you can do that with some RF or optical transition, for example. And then to see if there's a dipole moment, you want to reverse the electric field and see that there's an energy level shift between these two levels due to this now reversed electric field. The energy configuration is different. Okay. It turns out, so you want an electric field, right? These dipole moments are small, so you want to have a large electric field. For bound systems like atoms and molecules, large electric fields are had towards the bottom of the periodic table. These electric fields increase as the proton number cubed. So you might consider elements along the bottom of the periodic table because they have a large proton number, right? It turns out, all these elements are radioactive, and if you include nuclear spin, if you're going to look for nuclear T violation, the nuclear spin adds instability because you have an unbound proton or neutron in your system, so it's going to be even more radioactive. Okay, ion traps are nice for working with these types of elements because you need just a very small quantity and you can use that small quantity efficiently. If you consider the elements that can be laser cooled, I'm just showing the alkaline earths here. Of course, there's ytterbium and mercury. But if you take away an electron from these systems, these are nice laser coolable systems that you can control really well. And that, of course, includes radium. So radium has the same basic features as barium, strontium, and calcium, basically. Okay, except there's no stable elements anyways. Okay, radium gets this extra feature though. So, you have a nice enhancement because you're at the bottom of the periodic table, but it also has this special nucleus that's octupole deformed. Not many elements have such a nucleus. What this really looks like in the ground state, there's a parity doublet of this octupole deformation up plus octupole deformation down. you expect to find an opposite parity doublet somewhere. In radium, it's 55 keV above the ground state. Okay, that energy scale is pretty small on the scale of nuclear physics. The way that this enhances sensitivity to new physics is that these T-violating sources can mix these opposite parity states and leave you with something in the lab frame that looks like this. So that leads to an enhancement that's a factor of 100 to 1,000 times larger than, for example, mercury, which currently sets the best limits in an atomic or molecular system for these T-violating forces. Okay, you can go a step further and put the radium atom inside a molecule and utilize all the features of molecules that have had such success with ACME and the ytterbium fluoride and hafnium fluoride plus experiments. This is another parity mixing where you're mixing two opposite parity states to control the electric field inside a molecule and get a factor of roughly 1,000 enhancement compared to an atomic system. You can put these two stages of amplification together, so you can get the nuclear enhancement and the molecular enhancement, and really hopefully amplify some new physics. Okay, so how would this look? This is the type of experiment that we're working towards. We want to use just a single radioactive molecule controlled by a single ion that happens to be radioactive. Radium's a great match for this type of experiment. So we'd like to try and measure time reversal symmetry, and with just using this kind of simple system, which has some nice features. I would say that our work is really supported by so much work and thought from others. I would say on the kind of quantum technology side of things, the NIST ion storage group has really set the stage for how we would read out and control the internal state of this this molecule. Maybe I'll say more about that later. Right. We want to use a new technique for doing the measurement. This is an idea that Amar Vutha came up with, and I worked with him just a little bit on this paper. It's a technique that's generic to EDM measurements. You could use it with neutral atoms, neutral molecules, or these charged species. It has the nice feature that it's a dynamic polarization technique, so you can use it inside an ion trap and polarize something in an ion trap with it. Okay, and it should be compatible with a high frequency ion trap that we'd need for this type of work. Okay, so how do we do? I'm really simplifying down this T violation in terms of just one parameter. This is the theta QCD that's anomalously small. Naively, we expect this to be of order unity, but it turns out it's not. I'm showing you the best measurements of this angle in mercury, an atomic system, and with the neutron EDM measurement. Okay, so how would we do in a first kind of proof of principle experiment with 1 second coherence time and measuring for roughly 2 weeks? We'd expect to get to about here, which is pretty decent. We think that we can extend our coherence time of our measurement out further and start pushing down lower. And there's real potential for switching elements to protactinium and really starting to push the bounds on this T violating parameter. A lot's unknown about this nuclear structure, but it's possible that the energy level splitting I showed you before that kind of enhances this sensitivity to new physics is really small in this isotope of protactinium. I should say that there are a lot of experiments underway with sensitivity estimates all in this range. And that's really a good thing because in this oversimplification, I'm kind of leaving out a whole bunch of ways in which T violation can occur in a complex object like a nucleus. So really a lot of measurements provides a lot more value than just one single measurement here. Okay, and I should give a ton of credit to Nick Hutzler and his grad student Phelan. They are they're the people I call when I'm having trouble figuring out molecules, and they're the ones who have really understood kind of what are the best systems to, what are the best molecular systems to use, what are the best radioactive molecules to use for these types of measurements. I'll point out that, you know, our science states in this system, RASH, which has a interesting name, are separated by a really convenient frequency for the technique that we want to do. This is all really preliminary, but for us, it's really exciting. And I'll say a little bit more later about our flexibility in changing molecules. Like, we're not too worried about switching molecules, and maybe that will be clear towards the end. Okay, I'm about to jump into our work with radium ions and start showing you data and radium molecules. But if there are any questions at this point, I'm happy to answer them. There might not be.
Yeah, no, there are some questions so far, mostly from the panel, but that might partially be because I forgot to remind people that you can ask questions through the Zoom Q&A or via the chat box to the side of the YouTube video on YouTube. But we do have some questions. So John K. from our panel was wondering, without knowing the new physics that produces the electric dipole moment, is it possible to estimate the stability of the anti-aligned configuration when you flip this field? Or in other words, what are the conditions to prevent the dipole from actually just following the field when you flip it?
I guess I would say that your control over, I mean, roughly speaking, your control over the magnetic moment that's in the particle is really strong compared to any dipole moment control, if that makes sense. So, you know, we use a combination of magnetic, or we will use a combination of magnetic and electric fields to control the states of the system. I hope that answers the question.
Yep, John's giving the thumbs up. So, so Nick Hutzler actually was wondering, are there can you use highly charged ions of other radioactive atomic species? Are those of interest, and are they laser coolable?
Yeah, great question. So thorium-3 plus is indeed laser coolable. One of the earlier radioactive molecules that's been laser cooled. And indeed, if you go to highly charged ions, it's kind of intriguing that, you know, maybe this kind of shift moment won't be shielded as much. Maybe the technique would be make some really highly charged exotic atom and then do quantum logic spectroscopy with beryllium on it or something, like all the nice work with highly charged ions. Yes, definitely possible. It seems like it would be fun.
Okay, and then we have a question from Dima Budker. So he's wondering, why is the molecule with sulfur better than the one with oxygen?
Oh, great. Okay, sure. So this is why I call Nick. Okay, so RaOH plus, it turns out that this RaOH plus in this excited state is expected to live for about a second. So the excited state's some maybe 14 terahertz or something like this above the ground state. It's in this excited state where it's bent, and you get this doubling mechanism that gives you the science states. As Nick will point out, inherently bent molecules in their ground state are more of a rule than the exception. So these straight molecules are kind of more of an exception, like RaOH plus. So that's why RaSH plus it seems good for a really long kind of coherence time measurement. we don't have it at the top of our list just because it's, it's just kind of little studied. I would say, Phelan knows the most about it right now. Is, calculating away. Like RaOH plus is more of a known quantity, but can switch between them. Yeah.
Great. Okay, I think we can keep going for now and save the rest of the questions for later.
Cool. Okay, so here's what the level structure of the radium ion looks like. These are all nice diode lasers. I point out that the 468 nanometer light used for laser cooling is relatively far from the blue, which is nice. For laser cooling, you only need to drive these two transitions. And I should say at the start of this work, we had roughly 5 gigahertz uncertainties in these various transitions. And that almost that kind of uncertainty and trying to see light from this ion in a trap is a little bit, at the time, more nerve-wracking than anything associated with radioactivity. So nevertheless, here we go. So this is what our trap looks like. It's a big trap. You can see the cooling light and this repumping light coming in to intersect at the center. This green beam represents our ablation laser. So we load our trap with laser ablation, and then we collect the fluorescence at 468 nanometers. This trap, we'll come back to it, but this trap was really built for the first laser cooling and the first initial measurement. So it's really purpose built for that. Okay, my students, after scanning the lasers for a couple weeks, were able to see the first laser cooled radium ions. This is exciting for us. We were rapidly able to make chains of ions like you see with any other species. Now it's starting to look like kind of a normal ion trap atomic physics type experiment. But again, there are unknowns. So one basic question you can ask is, if I have some population in the ground state, say, and I drive it to this excited P state, what fraction will decay back to this ground state or down to this metastable D state? So we can use techniques developed by Hartmut-Hafner to measure this branching fraction. I would say that that's an overarching theme in all of our research. We get to use all these great tools developed by all the ion trappers to really make measurements fairly quickly. So you can just see we're repeating a fairly fast pulse sequence many times and just counting the photons at 468 nanometers that are emitted from this ion. And with that, we can fairly precisely measure this P1/2 state branching fraction. It's nice that our measurement agrees with theory in such a heavy atomic system. So we like having the opportunity to be able to benchmark theories in a relativistic atom with many electrons. We had to set out and measure a whole bunch of transitions. So, one of the transitions we had to find was this optical clock or optical qubit transition at 728 nanometers. This is a long-lived state. It lives for 300 milliseconds. So this is gonna be an important transition for us to use. The first step is finding it. Here's what that looks like. So this is what we see in the lab every day. This is a laser-cooled radium ion where we're addressing it with those two wavelengths. These are the PMT counts. We use a beam splitter to divide the light between the camera and the PMT. And you can see as a grad student tunes this 728 nanometer laser, the ion is jumping to this metastable D state. So finding that transition is pretty easy, and it's exciting for us. This opens the door to a lot of possibilities. Right. So then, we had to actually measure the frequency. This is indicative of how we measured a whole bunch of frequencies in our system. We just drive the transition and compare that transition to vapor cell spectroscopy that we do in parallel. In this case, in iodine, we also use tellurium for some of the bluer transitions. Right, so in terms of lifetimes and branching fractions, this is what the measurements were before we started. Here is where we are now. We will actually measure these p-state lifetimes soon, and we should get this out. These measurements, we should get these out fairly soon. Let's say, if you take a step back and you're atomic physicists and you're working with a more standard atom like rubidium or cesium, you largely take numbers like this for granted, right? But they're really important. They tell you how many photons you'll scatter per second from your atom. Like, it's pretty critical information. At a more advanced level, you need to know these types of values to calculate, for example, blackbody radiation shifts in optical clocks. So these are just fun to measure and important to know. We also measured a bunch of frequencies and drove a bunch of transitions. So for example, this is the clock transition. And we measured these frequencies with these vapor cells to the kind of tens of megahertz precision that makes an atomic physicist comfortable. Okay. This is just a summary of kind of the low level energy structure that you need to understand to work with this ion that we now understand pretty well. Okay, now we want to start using this this clock transition to control the ion and kind of pursue our larger science goals. So one of the first obvious things you can do with it is just drive Rabi flops. So this is driving population from the ground state to this excited D state and just cycling it back and forth, Rabi flopping on this transition. This is nice coherent control. We can use that same transition to address a motional sideband. So we can detune by a motional frequency of the ion trap and controllably remove phonons from the system, and we can cool this ion to its motional ground state. I should note that for the ion trappers, these frequencies are fairly low. I just want to point that out. So that's kind of interesting. Yeah, and we extract this population by the area under these two curves. We can take this a step further, so we can cool the system to its ground state, and then we can controllably address just, for example, this blue sideband. So if you address this blue sideband, you add a motional quantum. If you address this red sideband, you remove a motional quantum. So we can do that. We can drive this blue sideband and engineer a Fock state. So this is making an n=1 state and putting the ion into its excited state. I should what should I say? I should say, why are we doing this? This has been done by lots of ion trappers. For us, this is a key starting point for controlling molecules with quantum logic spectroscopy. And you might say, Andrew, you're not going to get anywhere with 80% fidelity for quantum logic spectroscopy, right? And I would say, yes, I agree. We're not going to get anywhere with 80% fidelity. So I just want to remind you that this is our trap. This is what we're doing all this work in. This thing is a tractor. It's made for the first laser cooling. We're kind of taking this tractor out on the highway and pushing it up to 65 till its wheels fall off. So there you go. We can make a clock with our system. So we can drive a bunch of 6 different symmetric Zeeman sublevels to make an optical clock on this S to D transition. You can see an inset of one of those sublevels and the Allen deviation for this clock. It's at least competes with hydrogen masers in kind of our initial our initial effort. Should say, why would you do this? Okay, why would you do this? The laser wavelengths are nice. The mass, the heavy mass can, reduces some of the key systematic uncertainties. So, reduces, for example, the second order Doppler effect, right? Which can limit some clocks. So that's kind of nice. Here's another feature. This is a little bit different in how we can start to use radioactivity now to our advantage. So this is a little bit where we're going. We're not doing this yet, but this has been demonstrated. This is a diagram of a thorium oven, okay? You can heat this oven up and you'll get a thermal beam of radium atoms. You can then photoionize them and load them in your ion trap. This work was done, this has been done by a Dutch group to do spectroscopy on neutral radium-225. I should say that that group has done a lot of work on short-lived radium ion, short-lived isotopes of radium ions as well. So what's the advantage here? Well, the thorium is radioactive, so it's continuously producing radium atoms, okay? They're continuously getting filled up in this oven. And when you heat this oven up, the thorium just stays behind and the radium trickles out, okay? Why does the thorium stay behind? Well, its vapor pressure is some trillion times lower than radium. So, any modest heating, the radium leaves, you're left with the thorium, and it just can continuously populate this oven. So you kind of have, a near indefinite source of radium atoms that is going to be pretty robust. If you accidentally heat it up too much, all your radium will leave, but then it'll get repopulated by more thorium. So that seems nice. For our purposes, that also gives us access to some really nice isotopes. So in particular, it gives us access to radium-225, which has about a 15-day half-life, and it comes with a nuclear spin 1/2. For trapped ions, this is really nice because this gives you these M sub F equals 0 clock states in the ground state manifold. And so this is nice for making an optical clock. This is nice for making a hyperfine qubit. And this nuclear spin 1/2 is essential for all the precision measurement I was discussing earlier. Okay. So yeah, it should give us access to some nice isotopes. And then at this point, once we have this oven working, this is really going to start to look like any other ion trap experiment. You're not going to use ablation anymore. Here's what the oven looks like. It's 3D printed with tons of inspiration from the NIST vacuum group. We plan on loading it. This is at Oak Ridge right now. So we have 2 of these at Oak Ridge right now, and they're going to load it up with these different 3 different thorium isotopes, which will give us access to these 3 different radium isotopes, and then we'll put some strontium in it as well. Our lab uses strontium kind of as a gentle precursor to all our radioactive work. Okay, so that should be fun. Are there any questions at this point?
Yeah, there are some questions. So Adam from our panel was wondering, when you're doing the lifetime measurements that you showed, especially of the clock state, do you have to worry about state mixing from the electric fields from the ion trap mixing in sort of shorter lived states into your long lived states?
That's a good, I don't have a fast answer to that question. I'm pretty sure the answer is no. Maybe, sorry, I have to think about that for a little bit. If we have some pro ion trapper, they probably could answer that in a heartbeat. I think the answer is no, but I'm not certain. I'll think about that some more.
Okay. And then Matthew Bogoslawski from YouTube actually is asking, what challenges did you encounter for ground state cooling in this trap?
Yeah, so I think the students in the lab really cranked up the stability parameters, and we're getting close to like the instability regime when they were doing this to try and get higher voltages and try and get higher secular frequencies in the trap, higher motional frequencies. Yeah, I don't know. I mean, it's definitely really pushing the limit. Like, for example, we weren't able to do EIT cooling with this system. They're just too many other modes, I guess, that are too really populated with a lot of thermal phonons. Like when you're operating at these low frequencies, there are a lot of thermal phonons in your system. But yeah, we'll come back to that later.
So I had kind of a basic question, which is, how much harder is it really to work with a radioactive element, and sort of like what half-life would be tolerable? Like how short is too short? Are there other things than half-life that I have to worry about that, someone who wants to go down this road should be aware of that we haven't thought about?
Yeah, sure. So the longest lived radium isotope lives 1,600 years. That's the isotope we work with now. That's the isotope we do all the laser, that we laser ablate and load our trap with. It is nuclear spin 0. So I kind of touched on this briefly, but if you add nuclear spin, you increase nuclear instability. If you look along the bottom of the periodic table, there's a bunch of elements that have nuclear spin 0. I'd say that we're not too worried about, we have to look into the toxicity a little bit more, but for example, we'd love to ablate protactinium, which has a 30,000 year half-life, a spin 0 isotope of it, and start making molecules of protactinium and investigating those. I'll say that a feature of radioactivity is you start to get access to weird elements. So actinium doesn't have many long-lived isotopes. Maybe the longest might be a couple weeks, but radium-225 decays to actinium, okay? It decays to actinium via electron capture, and we think that the recoil from that is gonna be gentle enough that we can keep that in our ion trap. So I would say, and then we can start looking at actinium chemistry, which is interesting for radiopharmaceuticals. So I would say that, there's just a whole bunch of opportunities on the bottom of the periodic table. And my students tell me that, we have this sample of radium that we're laser ablating, and, they say, yeah, we're just ablating a part of the sample right now that just looks like bare stainless steel, and we get plenty of radium ions in the trap, just ablating there. So I think, you can work at really low activities like a microcurie and do a lot of fun work. Hope that's not too long-winded of an answer. I guess one note is like 1 microcurie of radium, you can buy that on eBay as a watch. That's a federally exempt quantity. We have 10 microcuries in our trap. So it's not too big a deal.
Great, thanks. I think we can probably move on and save the rest of the questions for the end of the talk.
Sure, okay. Okay, so this is just going back to what we want. We want to have a radium ion and a radium molecule. How do we get there? Okay, one of my students, this is what a radium ion looks like in the trap. And one of my students, Mingyu Fan, was playing with one of our lasers, just detuning it, just one of the standard laser cooling lasers. And he saw that this radium ion got smeared out like this, okay? And we discussed that, and I said, okay, that's interesting. Why don't you just go ahead and play with that, see what it leads to. That looks pretty interesting. So he did that. He went with it, and he understood what was happening, why that radium ion was getting smeared out. So this is a plot of the spectrum of the S to P transition at 468 nanometers. If you've detuned your your 1079 nanometer light to the red of this transition. Okay, and so this dip here is due to coherent population trapping, and what that does is if you park your 468 nanometer laser on this negative slope, you'll get coherent amplification of the ion's motion that's bounded on either side by these positive slopes, which lead to laser cooling. So you get kind of like a nice amplified motion, and it's like, okay, well, this is pretty interesting. What can we do? What can we do with this? Well, it turns out that you can really accurately measure the secular motional frequency really quickly by just changing this single laser detuning. You can coherently amplify the motion, collect all those photons, take the Fourier transform, and get a really sharp Fourier peak. Okay, so what can we do with that? Well, we knew that we could make these types of molecules, or at least we thought we were making these types of molecules. So this is a Coulomb crystal of 4 ions. 3 of them are laser cooled radium ions, these bright blobs, and this is a RaOH plus molecule, so kind of our first precision measurement target. So we can see this really clearly in our ion traps. They'll sit there for a long time. And what Minyu did was he used this coherent population trapping technique to really carefully measure the frequencies and therefore the masses of the ions in the trap. So this is the measured secular frequency from the Fourier transform. You can convert that to a mass. This is our calibration peak with the radium plus, with just radium plus ions in the trap. We can do a calibration, and then we can controllably leak in methanol gas to produce this RaOH plus right here, or this RaOCH3 plus here. We can introduce the deuterated methanol to produce the deuterated analogs of these elements. I should point out that these are really nice molecules for precision measurement, and Nick and Phelan wrote a really nice article on why this element or this molecule in particular has really nice features for doing precision measurement. Right. So it was nice. It was really fun to submit papers and discuss this back and forth with Nick over the past several months or so. Okay. Right. So where are we going? This is, I showed you, we have this kind of tractor trap that's made for brute force radium work. This is the NIST wheel trap that's undergone years of development and was used to make a clock with extremely low systematic uncertainty. Using quantum logic. Okay, so this trap is designed for quantum logic. This is what we want to do. We want to have a radium ion and radium hydride in this trap and do quantum logic spectroscopy on this molecule and start to realize these really high levels of control and investigate these radioactive molecules, their internal structure. I should point out that our group is super grateful to Didi Leibfried and Dave Liebrandt from the NIST Ion Storage Group. Dave provided us the trap drawings and details that you need to know to order these really custom traps. These are some diamond substrates that are gold coated. A ton of work went into this, and Didi's been really instrumental and helpful in steering our choice of initial molecule and guiding us with what we should do in the lab to prepare for this and succeed with what will be a hard experiment. I want to point out that in regards to the choice of molecule, we're pretty agnostic. We can use the same laser to address kind of any molecule we put in the trap, okay? Because we want to utilize and use stimulated Raman transitions, just like the NIST ion storage group uses to do quantum logic spectroscopy. This is nice because, you don't care about what the excited state is. You just kind of care that it's far enough away that you don't populate it directly. And you can choose lasers to do that. This really highlights, we don't need to switch our lasers. We can use our radium lasers, and then, some far off resonant laser, maybe in the future a far off resonant comb, to really control the population and do spectroscopy on these radioactive molecules and switch from molecule to molecule. The trap, I kind of have left this out a little bit, but the ion traps are great. They don't care about the internal structure. So the trap doesn't care about the internal structure, and our spectroscopy doesn't care about the internal structure of the molecule. So that gives us a lot of flexibility to, pursue our precision measurement goals, and also to just explore more broadly kind of elements and molecules along the bottom of the periodic table that are interesting and definitely little explored. I just want to point out briefly that, a precision measurement with this kind of setup is interesting because, we can use this co-trapped atom, during our spin processing time, for example, to, really precisely measure the magnetic field. So, this should just give you an indication that we can really understand this environment very well, and hopefully understand or suppress any systematics that come up as we press along here. This is magnetic field data that we extract from our optical clock measurement. And this atom, as I see it, is really a resource that can be used throughout kind of precision measurement with this type of setup. I just, that concludes the talk. I really want to give full credit to, these are the two grad students that have really led the charge on all this radium work. They both came into the lab with no AMO experience. I came into the lab with a little bit of trapped ion experience at the end of my postdoc. I want to thank the NSF in particular for providing just absolutely, critical funding at an important time for our group, the single PI grant. And we've recently got funding, and we're really grateful for funding from the ONR for our optical clock work that's coming up and ongoing. Thank you.
Okay, well, thanks a lot, Andrew, for a really great talk. So there are some questions and more coming in. So Dima Budker was actually asking, why does the ion trap substrate for this new NIST wheel trap have to be made out of diamond?
I'm not sure if it does need to be made out of, I don't know why, I don't know if it needs to be made out of diamond. A really nice feature that it is made out of diamond is that a future EDM measurement with a polyatomic molecule is going to require a fridge, and diamond's a good thermal conductor at 4 Kelvin at low temperatures, and so that should help with like black body radiation, things of this nature that would be detrimental to the experiment. Yes, good question.
And then another question from the audience. Ariane was wondering, can you discuss your plans for implementing a clock state EM measurement in one of these molecules in radium?
Yeah, sure. So I mean, I guess imagine this is a polyatomic like this RaSH plus. What we would do is we'd use quantum logic to prepare the state of the molecule. Okay. According to the ion storage group folks, you can do this pretty quickly, say in like 30 milliseconds or so. So we can prepare it deterministically in a single quantum state. If you want, I can show a slide on quantum logic spectroscopy. But this is fairly well established for the aluminum ion clock, and now it's been really ported to to molecules in this work. In this work, they show optical pumping with a CW laser in a single rotational or in a few rotational manifolds, and then in this work they use a comb to pump higher rotational states down. So that should give you confidence that we can really accurately know the state of the molecule. So we can measure it, we can prepare it on the front end and read it out on the back end. For the EDM measurement, what we want to do is use this technique that Amar came up with. So we'll populate our science state and then drive it with an electric field and drive the transition between these states with a magnetic field that is phase controlled relative to that electric field. And depending on the sign of that phase, we'll see a difference in the Rabi frequency, and that gives us our EDM signal. And that would be the thing that would run for a second or 100 seconds, and then we just do quantum logic at the end of that. Yeah, I don't know. I think there's a lot of fun opportunities here. We can imagine extending to a few more molecules or running things in parallel with multiple systems. We'll see.
So maybe a follow-up question that I have, and that I guess Adam was also wondering about. So 100 seconds seems like a really exciting but long coherence time. I guess what is it that that makes that possible, and what's the path towards getting to 100-second sort of coherent interrogation time?
Yeah, I think low black body radiation, our system can't be pumped by too much black body radiation. You can't have obviously you can't have an excited state that lives shorter than that amount of time. Other than that, I think it's possible. I will say, if we can't reach 100 seconds, if we can reach 10 seconds, I think that's roughly where the Gilla group is projecting to go. Maybe beyond 10 seconds. I'm not positive. If we can only reach 10 seconds, it's for a trap system, as you guys probably all know, you only win as the square root of your spin precession time. So we'll still be pretty non-sensitive even at 10 seconds. I don't know, maybe 100 is too bold. We'll see.
Okay, well, I think that's probably a good place to end it, and we can people can take the rest of their questions to the post-seminar informal discussion with Andrew. But I'd like to thank Andrew one more time for a great talk, and the link for the post-seminar discussion has just been posted. So now I'm gonna hijack things here so that I can show this preview of the next upcoming talks. Hopefully you can all see this. So the Valmos talk next week will be from another Andrew Hauk, Princeton University. We'll be talking about synthetic quantum materials with superconducting circuits. And our sister quantum science seminar next week is Philippe Bouillet from Institut d'Optique, and talking about quantum sensors with matter waves from the lab to the field. So hope to see you at those talks. Thanks a lot for coming. And now we'll see you over in the informal post-seminar discussion.
Thanks a lot, Andrew. That was great.